In the next couple of lectures, we are going to see how easy it is to apply what we just learned to a real-world dataset. In fact, this real-world dataset is one of the most significant datasets of all time. This lecture is about Moore's Law. As you recall, Moore's Law is the observation that the number of transistors per square inch on integrated circuits doubles approximately every 2 years. In other words, roughly speaking, computing power grows exponentially. Some futurists, such as Ray Kurzweil, have observed that this pattern applies to technology as a whole, so that even when Moore's Law runs out for transistors, perhaps some new invention will appear to take its place. Maybe that will be quantum computing, AI, or something we can't yet imagine. Now you might be thinking, wait a minute, this isn't linear at all. If something grows by a constant factor over a given period of time, that's actually exponential growth. For example, it will grow from 1 to 2, 4, 8, 16, 32, 64, and so on. We can write the generic equation for exponential growth as c equals c naught times r to the power t. Here, c is the output variable, and that's the thing we're counting. C naught is the initial value when t equals 0. T is the input variable, which in our case represents time. And finally, r is the rate of growth. You can see that if t increases by 1, then c increases by a factor of r. This holds true for all time periods. So if I'm at t equals 1 going to t equals 2, I can find the next value simply by multiplying by r, and similarly for going from t equals 2 to t equals 3. Luckily, by taking the log of the count variable, we can turn this into a linear equation. Basically, we take the log of both sides, and we show that the log of c is a linear equation with respect to the time t. This is exactly what we want. So if we use linear regression on the log of transistor counts with respect to time, we should find that the rate at which transistor counts double is approximately 2 years. If you can't see how this works right away, it might help to substitute the variables in the previous equation with some more familiar variables. So let's replace log c with y. This will be the output variable. Let's replace log r with a, the slope. Let's replace t with x. This will be the input variable. And finally, let's replace log of c naught with b, the intercept. Now we just have y equals ax plus b, which is our linear equation from earlier. Note that I'm using the letter a instead of m for the slope, which is perfectly okay. At this point, the problem becomes exactly the same as our previous problem. As long as we can transform our dataset into a quote-unquote Excel spreadsheet, which has the log of transistor counts in the y column and the year in the x column, then our code for building, training, and predicting with the PyTorch model should be exactly the same as it was before. This is what we mean by all data is the same. As you will see, there is no difference in the model between this example with transistor counts and the last example with synthetic data. And you might wonder, why do I say this so often? And really, I just go by how often I get asked. So it's really you, the students, who guide what I say. If I find that a lot of students have a problem with something, then I will emphasize that point more often. So despite the fact that I repeat this constantly, students will still sometimes ask me, can you do an example on such and such dataset? And my response is, as always, the code is exactly the same, no changes are needed. Although, because this message is pretty effective, I think it definitely has helped a lot of students understand the idea a lot better. There is one caveat to this, which you will see in the following lecture. In order to use linear regression or any other kind of model in this course effectively, you should make sure your data is either normalized or in a small range of values and centered around 0 or at least near 0. In order to do this, we're going to subtract the mean and divide by the standard deviation. This makes it so that the sample has mean 0 and variance 1. Please note that in this course, we will use the terms normalize and standardize pretty much interchangeably. Standardize is a term that is used more in statistics, and it refers specifically to the case where you take a sample and transform it so that it has mean 0 and variance 1. This is opposed to the term normalize, which could refer to standardization, but is a more general term overall. For example, it could mean transforming your data so that it stays in the range 0 to 1. This is not the same as having mean 0 and variance 1. On the other hand, in cases like batch normalization, which you'll learn about later in this course, it does refer to the standardization operation. The real question is, why do I mention this as a caveat? Here's the problem. We're doing 2 transformations on our data. This is going to make it more difficult to prove that transistor counts double every 2 years. So here's a quiz question for you. Given that the equation for exponential growth is c equals c naught times r to the power t, what does r have to be in order for the transistor count to double every 2 years if t is in units of years? I would strongly recommend you try to figure this out for yourself before we move on to the next lecture. The next question you want to consider is, if we take the log of both sides of this equation, how does that value of r relate to the slope of the line? And finally, if we normalize the data in both the x and y axes, how does that affect the slope and intercept of the line? We'll go through these calculations in the next lecture in detail, but the main point is, we are not going to get the answer directly just by fitting a line to the data. For example, just because the transistor count doubles every 2 years, this does not mean the slope of the line is going to be 2. It's going to be related to the number 2 somehow, but to find out exactly how, you have to do the math.